Dane began land surveying in 2005, and on day one, he knew that he was a surveyor at heart. He loved the ability to be outside, perform historical research, perform mathematical computations, meet with landowners, cut line, investigate, and assist with legal matters, and learn new equipment and technology. Dane received his land surveying and training in certification in 2007, subsequently became a licensed professional land surveyor in the state of Maine in 2009. Dane is currently licensed in not only Maine, but also Vermont, Texas, Colorado, and Oregon. In all, he has gained over 15 years of experience working in not only many different states, but many different survey disciplines, including residential, commercial, ALTA, the energy sector, transportation, and construction. Dane is currently works as a professional land surveyor for the Colorado Department of Transportation. He's also, which I'll send out in this week's email that everybody kind of gets blasted with every time Dane presents, but he has the surveyor's manual that he's put together. And this is another section or two out of his survey manual that he put together. So as always, Dane, I appreciate your time and your support.
Yeah, no problem. It's the least I can do, Trent. So thank you very much.
Yeah.
And I just want to give a shout out. There's a gentleman in here called, his name is Daniel Oakes. And when you were reading the bio about us cutting line, I was doing it with that guy. So I just wanted to say hi. I just want to say hi, Dan.
How we doing, Dane? Just remember, you got to cut away from your body and not at your knee.
Yeah. I was showing a new hire how to use a machete, and in the process, I sliced my knee open. So, and Dan was there. I was literally training him how to do it, and I had to go hit stitches. So,
oh my gosh. There's a mentoring Monday session on how to cut line.
Yeah, there you go. So, yeah, everyone should be able to see my hand, paper, and then I have a PowerPoint off to the side called single double proportioning. Does everyone see that?
Yes.
Okay. If not, let me know. All right. So, yeah, let's get right into it. Today, we're going to do single and double proportioning. This is going to be pertaining to, you can apply single proportioning within meets and bounds states whenever you do in subdivisions and whatnot. But typically what we're going to be talking about is how to break down a section in the PLSS system. Okay. And we'll get right into it. All right. First off, I want to stress this point. If you're proportioning, there's something wrong. Okay. What I mean by something wrong is you were not able to find any monumentation or evidence of monumentation whatsoever. Okay. Single double proportioning should be the last case resort. You should not be doing any mathematics at all. If you go out in the field and you find existing monuments, or you find evidence of existing monuments or reference ties, if there's any kind of evidence that you can lean on to find that position of the lost corner, that's what you should utilize as opposed to math. Okay. So again, last case resort. It should be pretty rare that you're using this, hopefully. Okay. So I just want to really make sure that everyone understands that you shouldn't go out there and start proportioning, double proportioning, as a check to a found monument. Okay, or not holding a monument because you double proportioned to a different location. All right. Existing monumentation is going to hold, and it's paramount over everything. And this is last case resort. Okay. So no math if you have evidence. All right. So keep that in mind during this whole talk. All right. In public land survey system, you have, the breakdown of townships and sections and whatnot. So what I've always had trouble trying to figure out, when do you apply single proportioning? When do you apply double proportioning? I went through the manual, and I want to, the caveat here is this is, a very generic and generalized statement and list of monuments that we have here, our list of situations, okay? There's a lot of situations where you can deviate from this list, but generally speaking, in a perfect world, this organization of double versus single proportioning is what we should be utilizing, okay? So basically, to summarize this, quarter sections. So here's your section. All right. You have your northeast, your northwest, southwest, and southeast. Those are going to be your section corners. Then in the middle of those, you're going to have your quarter corners. You're going to have your north, your west, your south, and your east. Okay. You're also going to have a center. And then, so now you broke down your section into quarter sections, but you can go further and break them into quarter sections, 16ths, okay? So then you're gonna have your south and north and west and east and your center, and it's gonna go so forth and so on, okay? So pretty much whenever you should utilize double proportioning should be your section corners, okay? These right here are where you're going to be doing your double proportioning. The quarter corners are going to be simple. They're just going to be single proportioning. And then you're going to get the center of your quarter of your section. That's going to be done by an intersecting lines, okay? So the center of your section is simply going to be a line drawn from your west position to your east position, draw a line from your north position to your south position, and where those lines cross, that's going to be the center. That's a whole other talk that we can do one day, Trent, on how to figure out that center. Intersecting lines, you have to deal with slope and all kinds of stuff. That's some pretty good math involved with that. But centers are intersecting. Then you get your corners, which are double proportioning, and you get your quarter corners, which are going to be single proportioning, okay? Now, this is for sections, but also you have your massive 6 mile by 6 mile townships, right? You're going to be finding this will be double proportioning because it's the corners of a section. This is double proportioning, corners of a section. You're also going to be applying it to the corners of the township. Okay, so you got township corners that will be double proportion. Now, when you have a section that is along a township line like this, the BLM manual states you should not utilize monumentation outside of the township that your section is in to help establish monumentation. So you have this township over here, and if you're going to be figuring out this right here, you would not be using double proportioning on these corners because they're on a township line. And in order to use double proportioning, you would have to utilize monumentation and evidence in this township, which is outside the limits of this township. The reasoning for that is because these townships were surveyed isolated islands, let's say, okay? When everything was done, you know, they established, I did a talk on public land survey establishment, but you do your principal meridian, your baseline, then you're going to do your standard parallels, and then your guide meridians. And that crisscross that you do is going to create your quadrangles. And then quadrangles are broken up further into sections. And those sections are going to be, I'm sorry, into townships. And those townships will be surveyed individually. So once you get the perimeter of your township established, you really aren't supposed to exceed that to reestablish stuff within it, okay? So I don't want to get too much into all this stuff. I just want to make a clear statement that generally speaking, corners of sections are double proportioned, quarter sections are single proportion. Township corners are double proportioned, and you will not double proportion along the perimeter of your township. Okay. Again, generally speaking, there's always rules to break that train of thought. All right. Oh, and the center is intersecting lines. All right. What kind of evidence can you use? Remember the first statement uses last case resort? Well, you have all this evidence that you can utilize to help you reestablish a corner as opposed to doing math. Okay. In this, there's also, parole evidence too. You go out and the landowners, all 4 land adjoiners all come out and they say, no, they all tell the surveyor in agreement, no, the corner was that rock. That's how it's been for the last 200 years. My grandfather said that was it, blah, blah, blah. I mean, you got 4 people, all adjoining properties, all telling you that that's the corner. That you should probably lean on that more than doing math and ticking everyone else off, So, but I just want to stress that you have all this kind of evidence that you can utilize to help you establish those corners before you do anything with a calculator. All right, so let's get into single and double proportioning. Single, I think it's pretty easy, but this single proportioning, it's pretty much a ratio. Okay, you got to think of it in terms of a ratio. And this process will come up again and again and again throughout your mathematics during surveying. Okay. It's used in subdivision breakdown. It's used in degree of curvature with horizontal curves. You can use it with photogrammetry scaling, traverse adjustment, level loops, coordinate conversions. It's going to come up again and again and again. An example of this is, I mentioned photogrammetry and scaling. Okay. So you have a real life size plot of land. Okay. And plane flies over, is taking a photograph. So now you have a photograph of that same exact parcel of land. Okay. So on the ground, it's 1 mile long by 1 mile wide. And this photograph is, let's say, 6 inches by 6 inches. All right. And they depict the same thing. Well, in order to figure this out, this ratio between the two, if you know from a house corner to you have a house here to the fence corner up over here. We know that in the picture, that distance from this corner up to the fence corner is 200 feet, let's say. Okay. I'm sorry. We know in the picture, it's, let's say, 2 inches. Well, what would that translate to on the ground? How much is 2 inches equal on the ground? Well, it's a scaling issue. Okay. So let's do the math for it. So we're going to have the photo and the land parcel. 1 mile by 1 mile and 6 inches by 6 inches. And we know that the distance is 2 inches from the corner to the fence. House to the fence is 2 inches. All right. Well, first we got to establish what the difference is between the ground and the photo, or reality and the photo. Well, 1 mile is to 6 inches. And then, so we have the land and we have photo. We would have to convert, let's keep it in inches and miles. We can do that if we stay consistent, because I know it's to be 2 inches. My answer is going to be in miles, and we're going to have to do some division. Okay. All right. So, and we want to know how many miles is 2 inches. Let's do the math for that and give a calculator. the 6x equals 2. Two divided by 0.333. Okay, so 0.333 times miles, feet per mile, 5280 times 0.333, 1,758.24 feet. Okay, so 2 inches equals 1,758.24 feet. So what I did there was I create a ratio, and I'm going to break this down for you here in a second. But I just wanted to show you that what we're about to do for single proportioning is applicable to photogrammetry. It's also applicable to degree of curvature and level loops and all kinds of other operations, okay? So knowing this process like the back of your hand is going to help you out with a lot of other operations, all right? All right, let's get into how we do it. Okay, so the first thing we're going to have when we're doing single proportioning for public lands is we're going to have a measured distance and we're going to have a recorded distance. So on an old surveyor plat, it's going to tell you it's 80 chains, okay? 80 chains equals 1 mile. So we know we're going to have 5,280 feet. That's what the surveyor notes tell you, 5,280 feet. Now, you go out, all right, that surveyor note, he did that in 1929, okay? Well, we go out with RTK now, and we locate it, and we come up with 5,272 feet, all right? That surveyor was short by 8 feet. He thought it was a mile, but it actually wasn't, okay? And that's understandable. He was dragging a chain through forest or whatnot, and we have better technology. It happens all the time. I guarantee another surveyor is going to go out there and he's going to measure it. And he's going to tell us we're wrong. It's really 5,271.98. Okay. All right. So it's always going to be changing is what I'm getting at. So we have what the record tells us, and we have what our new measurement tells us, record versus measured. All right. Now we have 2 types of measuring though. Now, or 2 lengths that we're dealing with. Let's take a subdivision. All right. We have a block in a subdivision and it has 3 equal lots. So here are block corners and here are our lot corners. The original surveyor back in 1928 said that the distance across the block is 300 feet. Okay. And the intent was to evenly space these lots out at 100 feet apiece. So this is all record information we got here. All right. Now we go out and we find those original block corners and we measure between them. We find no lot corners though. These rebar are gone, but we measure between them and we say it's 298 feet. It's not 300. It's in fact 298 feet. It's 2 feet shy. So where should these lot lines go then? We got to reestablish these corners right here and we don't know where to put them. All right. So this is record. This is measured. And we have 2 record. We have the total distance and we have the proportioned distance. So total is 300 and proportion will be the 100s. Then we have measured. We have measured total, which is the whole block length. And then we're going to have measured proportions. That's going to be our X value. This is what we're trying to figure out. That's the unknown. All right. So if you make a matrix of this, you have record and measured, and you have total, and you have proportioned. And you just simply fill in the blanks, and then you cross multiply to figure out your answer. So record total. What did the original surveyor say the total was? 300. Record proportion. What did the original surveyor say the proportion distances were? 100. Measured total. We measured it to be 298. And what are the measured proportions? That's what we don't know. So now we just cross multiply, and we're going to solve for X. So 300X equals 298 times 100, 29,800. Divide both sides by 300. X equals 99.333. Okay. So that's our X value. That's the distances we're going to place right here. Okay. And this makes sense. If the original surveyor thought the whole distance was 300, and he divvied it up evenly with 100s, and we come and we measure it to be 2 feet shy, then our proportion distances should be smaller than what he said, and they are. Okay. Another way to check this, if I were to add the distance, the difference from 100 to this, which is 0.77, I'm sorry, 0.66. If I were to add 0.66 3 times, I should get the distance, the difference between these two. 0.66, wait, 99.33 minus 100, 0.66 times 3, I get 2, which is in fact the difference between my measured and his measured. Okay, so that was a good check, and it's easy to do if you if there's only 3 lots like this. Well, it's easy to do if there's, I guess, 22. You could just multiply that times 20. But what I'm getting at is that's a good check. And also another good check is a smaller distance is going to warrant smaller proportions. If this was 301, then my distances would all be slightly over 100. Okay. So that's single proportioning. And this right here is the key. This is the matrix I'm talking about. You have 2 types of measurements, record and measured, the original and now, and then you have 2 lengths that we're dealing with, total versus proportion. So lengths and measurement styles or types, all right? And you fill in the blanks and simply solve for X. This right here is a breakdown of what we just did. In this case, it was a 200-foot wide lot block with 50-foot interval lots. That was the original record. We go out, we measure 202. So I fill in my matrix. This is measured. Oh, and by the way, you can flip these and you can flip these. It doesn't matter. Okay, as long as you stay, once you've established your matrix, stay in line with what you're doing, what it's calling for. Okay. What are those old, when I do this, I think of in biology class, whenever you would do the genetics, you know, you would you'd have the phenotypes, and you'd have one gene that forget the name of all this, but you know, one gene is recessive, one's dominant. Then you have, if it's recessive, it's blue eyes, and if it's dominant, it's brown eyes or whatever. And then it was like this little matrix where you could fill in, you could tell what were the odds of you having a child with blue eyes versus brown eyes, okay? It's kind of exact same thing. It doesn't matter if you put brown and blue or blue and brown, as long as you stay consistent. And in this square, whatever you established, you're going to put the proportion and the measured in that hole, okay? So again, flip them all you want, as long as you keep your lengths on one side and your measurement types on one side. So on this case, it was 202. So in my matrix right here would be measured total, and this would be record total. This would be measured proportion. This would be record proportion. Okay, so I did flip it from what I gave the example before, and it still works out. Set the matrix, cross multiply, solve for X, you're going to get a value. And this situation, my measure was a little bit larger, so my interval, lot interval measurement should be a little bit bigger, and sure enough it is. It's 50.5 versus 50, all right? So again, this matrix is the key. Now, this is the key for single proportioning, but it's also important in double proportioning, because double proportioning, we're getting to right now, essentially is single proportioning twice, all right? So we'll get into that, but before we do, let's introduce you to double proportioning. Double proportioning is, like I said, single proportioning twice. When performing double proportioning in regards to sectionalized land, the use of cardinal equivalents is paramount. So a cardinal equivalent is what you've always known as a lat and a latitude and a departure. Okay. So let's take this. So you're measuring from this point to this point, and this is due north. Okay. So this is the distance that we measured. Let's say that distance is 110 feet. And that's all great and stuff, but we want to know what the cardinal equivalent is from this point to that point. Well, break this up into a right triangle, and you're going to have a distance that from this point to this point, the distance of change in a pure east-west direction, due east, due west direction, and you're going to have a change from this point to this point in a due north and due south direction. All right. So the change in the due east, due west is what we call departure, and the change from due north and due south from point to point is called the latitude. And these can be solved pretty simple if you know this angle. So you're going to have to be provided an angle. Typically, we're given it in bearing form. North, 30 degrees east, let's say, for 110 feet. Well, north 30 degrees east, north 30 degrees east, I measured down 30 degrees. I know this is 90, so this will have to be a 60-degree angle right here. So now I have an angle, and we're going to use sine, cosine to figure out these latitudes and departures. So to figure out, now I have my hypotenuse already. That's 110 feet. So let's solve for the latitude in this situation. It'll be 60 degrees, so sine of 60, which sine is opposite over hypotenuse. Sine of 60 degrees equals opposite over hypotenuse. So sine of 60 times 110. .26. So latitude in this situation will equal 95.26. I obviously did not draw this to scale or the right angle. All right, let's do departure. So departure would be cosine of 60 degrees equals adjacent over hypotenuse. So departure over 110. So cosine of 60 times 110 equals 55. So my departure equals 55 feet. So given this situation, again, it's not to scale. I didn't draw this angle right, but in this situation, this distance would be 95.26 feet, and this departure would be 55 feet. Okay. So that's how you find the departure. Now, and latitude. So this is going to become important. If we do this process while figuring out the math of a double proportioning problem, the end result will be the coordinate of the new position. And the reason I'm saying this is because technically, so you have your points here. Let's say that we're doing a double proportion. We have our lines. And so what you do is you would single proportion this distance. You come out with a position here. Then you would single proportion this distance, come out with a position here. And the BLM manual tells you that you would need to go due west or east, in this case, due east and due north. And this right here is the true location. It's not going to be here. The only time that that's the case is in the center of a section. Okay. We're going to go into all this next. I just want to clarify this. So the BLM manual requires you to single proportion this line, come up with the location along that line, single proportion this line, come up with the location along it, and then go due north or south and due east or west to make your intersection of your corner. Okay. Now, if we do our departures and latitudes up front, that position will be revealed in our solution. Okay. If you can draw it out drastically. So if I were to do something like this, something like that. Okay. And I'm finding out my departure for this line and my latitude for this line. I'm going to come out with an answer right here. Now this is drawn out drastically, but all I'm trying to say is we're going to do what the BLM manual requires of us if we follow the steps I'm about to show you. And the way that we can do that is we're going to figure out we're going to proportion the departure and latitude as opposed to figuring out along the actual line. Remember in my example, that line that was 110 north 30 degrees east. We're not going to single proportion along that line and then go off of it later. We're going to figure it out up front where the location is. Okay. All right. So let's get into a good example of all this. Just want to stress again, cardinal equivalence is how you find the true answer for double proportioning. All right, so we went over departures and latitudes, but that's what I'm doing here. Okay. Now we're going to have 4 lines that we're dealing with. Okay, 4 separate lines. We're going to have 2 lines for our east and west line, and we're going to have 2 lines for our north and our south line. So it'll be a total of 4 lines. The hardest part about double proportioning for me is keeping everything organized. If you can keep it well organized, then it's pretty simple math. It's just a matter of keeping it organized. I have some good notes over here, but basically we're going to break this thing down into right triangles so that we can work with something that we're familiar with and we feel comfortable with. Okay. To me, right triangles are essential for 90% of math that we do as surveyors. All right, so this is a breakdown of a situation that we're gonna solve for. So we have, let's say we have a corner that we're missing. Okay, unknown position. We have a section corner here. We have a section corner here, section corner here, and section corner here. And this right here is the intersection of 4 separate sections. Let's say it's section 1, 2, I don't know what they would be, 3, 4, 5, 6, 7, 8, so it'd be 12 and 11. All right. Now we would apply double proportioning to this because, again, remember one of the first slides, it said that section corners are applicable. All right. In this example that we're showing, it's really, they were utilizing quarter section monuments. Okay, so this right here is the true example, which is fine because quarter sections were on that list of evidence that you can use to double proportion with. So we have something that needs double proportioning because it is a section corner, and we have viable evidence surrounding it that we can utilize. Now, it might not be this pretty. There might be a situation where you do have to use a section corner on this side as opposed to a quarter section corner. All the math is going to apply. Everything is going to be the same. It just might get a little tricky, okay? More to keep organized. So the goal here is to reestablish this corner, and we have these monuments to do it with, these quarter section monuments. And these are the 4 lines that I was just talking about. We have this line, the north line, we have the south line, we have the east line, and the west line. Those are all going to converge in one spot with single and double, with the double proportioning. Okay. From this diagram, the example, they're going to have to give you pretty much all this information during an exam or whatever, or in reality. You're going to have some angles provided to you. You're going to have some record distances provided to you. The only thing you're not going to have is going to be your measured proportion, which is typically your X value that we already talked about during the matrix. So we're going to have, record and measured, total and proportion, and we're just going to fill in that grid. This example, it gives you the total record. It gives you the proportion record. We know the measured total from our coordinates, but we do not know this one. And that's typically the way it is. We don't know the measured proportion. 9 out of 10, that's going to be your variable. All right, so let's get into the actual problem. Step 1, from that example, we need to find the record calls. From the record calls, we need to figure out the record latitude and the record departure for each one of our 4 lines, okay? 2 for the north and 2 for the south. So back in here, we have a record total for this whole line here. From this point down to this point, we have a record total. Now we can't use along the line. We have to use the departure and the latitude for it, but we can easily find that. And that's just what I showed you just now. So let's solve step 1. Let's solve for the north latitude record length. So we have a situation where it's from the quarter section we're going to the record called original position. We have a line that is north 0, 0 degrees, 0, 1 minute east. And the original survey note said it was 40 chains. All right. So we know northeast 1 minute. From that, we can derive our angle, this angle right here. Well, we know it's 1 minute. So I'm going to convert 1 minute to degrees minute to decimal degrees. 0.01. It's equivalent to 0.01. The angle here is 0.016666. All right, that's our angle. Now, this is the north line. We have a south and west and east. On our north-south line, okay, we're gonna, you have a lot of different lines. You have 4 lines, but on our north-south segments, this one and this one, we do not have to worry about solving for departures. We only have to worry about solving for latitudes. Remember, latitude was the north-south direction. Departure was the east-west direction. So on our north line and our south line, we only care about latitudes. And the opposite is true for our west and our east line. On our west and our east lines, both of them, we're going to be solving, we only care about departures in that situation. So that's going to save us a lot of time. We don't have to find latitude and departure for all 4 lines. We only have to find one or the other depending on their position. So our north line and our south line, we only solve for latitude. On our east line and our west lines, we only solve for departure. So that's going to cut our work in half, okay? So we have to break down 4 right triangles, essentially. So we have our angle on this one. I want to figure out, I only care about departure. I only care about this line. I don't care about this line. So that's going to be my cosine over my angle. And I know my distance is 40 chains. So my hypotenuse is 40. So cosine of 0.016666 cosine times 40. My departure in this situation right here, I'm sorry, my latitude is going to be 39.9999831. Okay. I'd recommend using your memory on your calculator, because this amount of small change, because this is a very small angle. Okay. That small change, it's going to fluctuate our significant digits. So I would recommend using memory on your calculator as opposed to punching in all these numbers every time, especially when you're rushing through an exam, okay? So now on this line, so that's my north line. I'm done with the north line. Now on this line, the distance and bearing was northwest 2 minutes, which is the same as southeast for 40 chains. So I do the math, I'd figure out this angle. I multiply cosine times that angle to get my latitude on my south line. On this one, I'm going north 89.58 west, 89.58 northwest for 39. So the record says 39.94. Now in this situation, I only care about my departure. I only have to solve for this line. I don't have to solve for this one. So I'd figure out my angle here. Northwest 89.58. That would mean I only have a 2 minute angle here. So this would only be 2 minutes. So it'll be cosine of this angle times my hypotenuse length record, and I would get my departure for this line. Then I would do the same thing for this line, figure out the departure based on the bearing and the length. So now I have 4 values. I have figured out 4 separate values, one for the north line, one for the south line, one for the east line, one for the west line. Okay. Let's say my north line, well, let's not say it is 39.9999831. And let's say my latitude for the south line is 39.992, let's say. Okay. So what I have here, by step 1, by breaking down these right triangles, figuring out my departures for east-wests and my latitudes for north-souths, I have figured out 2 parts of my matrix. Remember, I have measured and record. I have total and proportioned. Well, I've already figured out 2 of my holes for my matrix. I figured out my measured total and my measured proportion. My measured total is going to be the distance from here to here, which is going to be this latitude plus this latitude. So if I add those 2 up, I have this filled in. I also have 2 proportions. I don't need them both. I'm going to pick and choose which one I want to use. Let's say we choose this one. And I'll show you, this is going to be like step 3 or 4, but I'll break that down. So I actually have 2 I have more than I need, and I'm only going to select one of them. I like to choose the south line, and I'll show you why. 39.992. Okay. So from step 1, I've already figured out half of my graph. Half of my matrix. Okay. That's step 1. Does anyone, this is the hardest part. If you can get through step 1, you can do the rest. Like a 3rd grader can do the rest of the math. Okay. So, does anyone have any questions about this part right here?
Anybody can unmute themselves if they want to ask.
All right.
You got nothing.
Good. All right. All right. So that's step 1. And from step 1, again, we already conquered half the matrix. All right. Step 2, very simple. We were provided coordinates for each one of these monuments that we're coming off of. Okay. We have a northing and an easting. All right. So think about this. Let's take our north-south line. We could do a lot of math and try to figure out, a distance and a bearing from this point to this point. We could do all kinds of COGO measurements. COGO operations. Okay. But if you really think about it, and we're really trying to break this down into latitudes and departures, just like with record, with the measured part, we only care about latitude for our north-south line, and we only care about departure for our east-west line. So if you really stop and think about it, you have a point, let's say just a normal Cartesian graph, and you have a point at -1, -1, and a point at +1, +1. Okay. So y-axis and our x-axis, 1, 1, 1, 1. So I could figure out the distance right here if I really want, but that's not what I care about. What I care about is this distance right here. That's all I really care about. So if this is -1, -1, and 1, 1, all you really got to do to figure out that distance, it's already given to you. This is your X value. This is your X value. This is your Y value. This is your Y value. So I have -1 to 1. What's the distance from -1 to 1? Be 2, right? I go 1, 2. So I already figured out my departure just by using the Y value for this situation. Well, remember, X and Y converts to easting and northing. So you got to flip them and make it northing and easting. So if you go here, and I have a northing and an easting and a northing and an easting, if I just simply take my northing of my northernmost point and my northing of my southernmost point, and I subtract those two distances, if I subtract 5,000, my northing value here, from 10,177.52, I'm going to get a value that is going to be my latitude for my measured, because these are measured, new, recently found measured coordinates. So if all I care about is latitude for this line, all I got to do is subtract my northing from my northing, and I'm going to get a value, which is going to be my latitude. So in this situation, it's 5,177.52 feet. So my departure, my latitude for my northern line in this situation is 5,177.52 feet. Well, that just filled in. This is my measured total. That just filled in another part of my matrix. And I only have one left, which is going to be the unknown anyway. So I have everything I need to know now to figure out my proportions. All right. So going back to measured totals for my east and west line, now I can scrap my northings and I just have to deal with my eastings. Just like this example, now I only care about my X values, not my Y values. So I only care about my east values, my easting values, and not my northing. So if I take this number and subtract this number, I'm going to get a value. It'll be a negative if I do that, which just take the negative sign off. Or I could do 7642.99 minus 2366.38. I'm going to get a value, and that's going to be my departure for my east-west line, which will be my measured total for my east-west line. So step 2 is pretty easy. Step 2 is just simple subtracting northings and subtracting eastings to get your latitudes and your departures accordingly. Okay. So again, now we have the matrix all filled out. Step 1 took care of 2 of the holes. Step 2 took care of the remaining hole. Now we just got to do the matrix and start solving for our proportioned measured distances. All right. That's where step 3 comes in. So this is a breakdown of what we've been doing. This was the record breakdown. So record, I did this operation 4 times. I only cared about latitude for my north line, only cared about latitude for my south line. Then I only cared about departure for my east line. I only cared about departure for my west line. I got 4 separate proportional record values. If I add up my 2 northing, if I add up my 2 north and south, and I add up my 2 east west, now I have my record total distances. And we did all that just by simple right triangle breakdown. Okay. Then step 2 was simply subtracting northings to get my departure. To get my latitude for my north-south line. And then we only cared about eastings, subtracting one easting from the other to get my departure for my east-west measure. Okay. So that takes us through step 2. Now step 3. Now we got to start plugging in all these values we've been finding into our matrix in an organized fashion to start figuring out what kind of values we need to add or subtract. And so let's go through that process. All right. So measured, record, total, proportion. All right. Let's take our north-south line. So it looks something kind of like that. All right. Our measured total, that's the value we got from subtracting northings from each other, and we got a value. Remember, it was 5,177.52. And we just got that number by subtracting this northing value from that northing value. That gave us our latitude for our measured total. Step 1 gave us the record total. So we broke that triangle down, did all the sine cosine for it, and we figured out a distance here. That was our latitude record. And we did the same thing here, record latitude. And if we add those two up, those two values up, we're going to get the record total. And if we added those two up, it came to 79.999999154. This is going to be our unknown. Now, this is the key. Which record portion do we want to use? We have two. We have this one or this one. You can use either one. I like to use the south one. Because if we use the south one, we're going to come up with a number, and we just simply add that number to our northing. If we use the north one, we're going to have to subtract that number from the north point. Okay? It all depends what direction you want to go. Both of them work out. The math will work. You just have to know what to do with the number that we get from this matrix that we're solving, that we're going to solve. So again, let's just use the south, and I'll show you how to use that value or the result. Okay, so the record portion is going to be the latitude that we solve for our south line. In this situation, it's 39.99999,323. Now I just got to cross multiply, solve for x. In this situation, x, if I do the math, it'd be this number times x, that times that, I'm gonna get a number, divide that number by 79, and we get 2588.76. All right. So this is the number that we came up with. That is the value that we have to add to this points northing to get a new measured proportion. So this points northing down here is 5,000. This point was 5,000, 5,000. So if I add this number, northing and easting, if I were to add this number to that, I'm going to go up, right? I'm going to increase my northing, means I'm going to be going up, which is what I want to do. If I were to subtract this number from this northing, I'd be going down. Our goal here is to get in the middle of our two found points. Well, how do you get in the middle? You would add that number to this northing to find a point in the middle somewhere. Let's say this value, let's say I derive this value by using this one, this northing latitude for my record, okay? Well, I would have came up with this number, and if I add that to this, I would go even higher than that point, which wouldn't work. Again, we're trying to go in the middle, so I'd have to subtract this value from this northing to get a point in the middle. So what you want is you want a value that is in the middle of this northing and this northing. We don't care about eastings when we're dealing with our north-south. We only care about northings. We only care about northings. We only care about latitudes. So I use my south proportion record, which means I'm going to have to go in the middle, which means I'm going to have to add this value to this northing, and it's going to be 7,588.76. So I don't know my easting yet, but I know the northing of my final point is going to be this. All right. Now we would do the exact same thing for our east-west line. Set up our matrix, measured, record, total, proportion. All right. Measured total. Measured total in that situation would have been the difference from eastings, which was step 2 for this value. And we came up with 5276.61. Our record total, that would be figuring out by right triangles in step 1. We figured out the departure difference, that distance and that distance, and we added them together. So I would do the math for this west line, do the math for this east line. I'm going to come out with a departure for here and a departure for here. Those are going to be my, if I add them together, it's going to be my record total. In that situation, it was 79.96996614. This is going to be my unknown. This is what I'm trying to figure out, as usual. Now my record portion. I have 2 to pick from. I don't care which one you pick. You just got to know what to do with the value once you solved it. Let's pick, in this situation, I do pick the west one. So let's pick the west one. So my record departure is for that line was 39.93999324. Cost multiply, I come out X equals 2635.336. So that's my result. I got to know what to do with it though. I want to come out with a coordinate that is in the middle of these 2 points. So I would have to subtract easting to go easterly from this point. And I would have to add, wait a minute. I'm sorry. I'd have to add an easting value. I'd have to add this value to my easting to move to the east from this point. And I would have to subtract this value from my western easting to get a point in the middle. So again, if I were to use this departure, I would be subtracting the number. If I use this departure, I'd be adding it. We use this one, so we'll be adding. So my easting over there, my easting for that point was 2366. Let's see. 2366.38. 2366.38 plus 2635.336. Add those 2 up. I'm going to come out with a value that's 5,000 something, which is in the middle of these 2 points. That comes 5,001.72. So that's my easting value. So now I have my easting and I have my northing. Put the northing and the easting together, and I have the coordinate of my unknown point. This is the answer right here. Okay. I have a diagram here showing how that works. So I have a point here and a point here. This is what I wanted to show you, the cardinal equivalent. So by doing what we did, we've already taken care of the cardinal equivalent. So normally you would have a line that we proportioned and a line that we proportioned east-west, a line that we proportioned north-south. So I come out with a value here and a value here. And then normally you would have to go do east-west, do north-south to figure out the missing point. Well, we figured out latitudes and departures the whole way through. So if we come up with a value for this, we have a northing and an easting value for it. We have a northing and an easting value for this one. If I just use my easting from this one and my northing from this one, which is what we did, we're going to get a value for this that's correct. Okay. So if you look at the diagram, if we know the northing right here is -1, -1, the northing right here is 2, 3, X, Y flipping, you got to keep track of that. This would actually be 3, 2. Then if I know that my easting has to be -1 and my northing has to be 3, well, then I know the value of this is going to be 3, -1. Okay. Just like in reality, it's 7588.76 northing and an easting of 5001.72. Okay. So this is just a recap. I have it all colorized to show you the steps that we've taken. So step 1 is dealing with the yellow and the green. And what we're doing in this situation is we're figuring out 2 things with step 1. We're figuring out the totals for the north-south and the totals for the east-west. And we're also figuring out the proportion. We kind of figure out the total by default because we broke it down into 2 separate portions. Add them together, you get your total for your record. So step 1 provides record total and record proportion, 2 parts of your matrix. Step 2 was dealing with coordinates. That's your measurements. We only care about eastings for east-west. We only care about northings for north-south. Simple subtraction will reveal the distance of departure for your east-west and your latitude for your north-south. So that's step 2, and that figured out the 3rd part of your matrix, the 3rd and final part. Step 3 was put in all that information in an organized manner to figure out your measured proportion. All right. And that's just using the matrix. Fill in all the information that you got from steps 1 and 2. You're going to reveal a number in step 3. You have to do this twice. And the reason you're doing it twice is because you're double proportioning, which is essentially single proportioning 2 separate times. All right. You're going to come out with a value. Then you have to know how to use that value. Again, your value, the number you're aiming for, is always going to be in the middle of your north-south and the middle of your east-west points. So you're going to have to either add or subtract depending on what portion you used. If you always use the same one, I always use west and I always use south. That way I can always add the number as opposed to subtracting it. But just understanding you're moving east from your west point, you're moving west from your east point, you're moving south from your north point, and you're moving north from your south point. If you keep that in mind, you'll know what to do with that value. But that is step 4, is plugging in that value, which reveals the northing and the easting parts of your final point. And that's pretty much it. Does anyone have any questions?
Anyone? How about, do you have a diagram possible, or have you even thought of one on what 2 single proportion and what 2 double proportion? You know, say 16th corners or.
Oh yeah. This right here.
What do you got?
This thing.
No, like on, you know, on what situation would you do a single proportion? Oh, there you go. Yeah, yeah. Okay.
Yeah. Yeah. So you would single proportion everything on here.
Yep.
Except for your section corners, which are double proportion. And then all your centers will be intersecting lines. Yeah, is that what you meant?
Yep.
Yeah.
You're good. You're good.
Yeah, this is in my manual too. All this math, this exact example, everything's in that manual. So yeah. I mean, if you really stop and think about this, people, it's just multiplication. So we got cosine, we got sine, we got multiplication, we got division, and addition and subtraction. That's all there is to this. It's just knowing what to do when and to keep things organized. That's it. Knowing when to use it and staying organized. But I mean, literally, you know, 6th graders can do this. And don't
how come there's so many court cases over?
Yeah, I know. Yeah, good point.
That's funny.
Yeah. Yeah. Step 1 actually should be when you go out and there's a lost monument. First of all, do y'all know the difference between lost and obliterated and all that? So you gotta, you know, you're only applying this to lost monuments. Lost mean there's no evidence to put it back in. Obliterated, it might not be there, but you got 3 reference ties to build it back in, right? So that's obliterated. Lost is you don't have the monument, you don't have the references, you don't have people helping you out, you don't have a divot in the ground where it used to be, there's nothing. Okay, that's lost. So step 1 should be, if it's lost, just tell the client no thank you. You know. But
that's awesome. I love it. Does anybody have questions? If not, I'll definitely, as I always do, I'll throw up the WestFed videos in your manual and the link to your manual and all that kind of stuff. So
all right. Yeah, thank you.
Of course, of course.
Yeah, I hope that helped. So if anyone has any questions, reach out to me. You provide my contact information, don't you, Trent?
I do. Yeah.
Okay.
I will throw that in. George, you got something?
Sure. You also have to realize, as part of evidence, you have topo calls in the survey notes that can be used to reestablish positions too, besides actual bearing trees and witness corners.
Yeah.
And things like that. And you know, a lot of times they're phony as heck, but you know, you have to look at that and you have to try and apply them. And you know, sometimes they work and sometimes they don't. But
yeah,
if you don't go there, you know, you're missing out.
Yep. Yeah, no, again, you should be utilizing everything you possibly can. Yeah, topo notes, you know, distances from barns, distance from a rock pile along the line. I mean, there's all kinds of stuff you can fall back on. And that's why there's court cases, because people get there, they stay in their little groove, they look around, there's nothing here, let's just proportion it. Meanwhile, there's a beautiful whatever sitting 20 feet away that could have been utilized, you know?
We have lots of corners here in Nevada that are a rock mound with a wooden post that turn out to be pebbles and a stick.
Yeah.
And
yeah.
I think Trent's seen a few of those down south.
Yep.
Yeah.
But you know, you're up against it when you're looking for those, but you gotta go through the motions. You gotta be thorough, and I know I've missed a few, and knock on wood, so far it hasn't come back on me. But it's easier to miss them than it is to get them right sometimes.
Yep. Yeah.
Go for it, Danny.
So I got an interesting question. I'm working on a survey right now where one of the corners would be the southwest 16th corner. And in the absence of any real monument evidence other than the opposing corners that I could proportion from, the only other thing that's there is some fence corners. And I knocked on all the neighbors' doors, and of course, nobody knows where the corner is, right? They all point to a different fence post and say, I think that's it. So at the end of the day, I need to possibly proportion this corner. And a question I have is, I was always under the impression that 16th corners are just single proportion. And that's just, I guess I just wanted to talk to the throbbing brain and make sure that I'm proportioning that properly.
Yeah, I think so.
Okay. It's always been my impression too, but I'm just posing the question in case the throbbing brain has a different opinion that I need to maybe double proportion a southwest 16th.
No, I don't think, I mean, you might have to double proportion the southwest section corner to be able to utilize to figure out your single proportion. You know, if you're gonna have to build that, if that's not in, if you still see my diagram, if your southwest isn't in, you're gonna have to put that in first and then build off to figure out. So yeah, you will, if that's not there.
That southwest corner is there. All the other corners are there for me to single proportion that southwest.
Oh, well then, yeah, no, you're golden then. If you got this and you got this, it's just a simple single proportion.
Yep.
Do you agree, Trenton?
Yes, I do. Yep.
Yeah.
Yeah. Sorry, Danny. I was gonna wait.
Yeah, no worries. No worries. I sent you the question because you're moderating, so I thought maybe you would pose it. Yeah. Yep. Cool. Thanks, guys. Appreciate it.
Of course.
Yeah.
It's the Wild West out here in Colorado.
Yeah.
Anybody else? Nobody?
All right.
Dane wants to get back to painting.
Yeah. Yeah.
Awesome.
The rain stopped, so I'm good now.
Oh, there you go. Good to go.
All right. Well, thank y'all. Thank you very much, Trent.
Of course. I appreciate it.
Thanks.
Have a good week, everybody.
Thanks, Dave.
Yeah. Thank y'all. I'll be here next month in September. What am I doing then?
What did we do? I forget.
It's all right.
Let me see. Next week, we got an author who had wrote on a book on von Schmidt, which is all about.
Oh, okay.
So that's gonna be cool. Let's see what do we have. Rules of construction.
Oh, all right. Good. Yeah, that's a good one.
Yep.
All right.
Awesome.
Well, thank y'all.
Are you headed north, Trent? This weekend? Are you headed north this weekend?
Nope. Nope. I'll be back home. I got granddaughter's birthday this weekend, so.
You're staying home?
I know.
What the heck?
Well, that's not exactly. I am running a half marathon on Saturday morning and that's going to be in Beaver, Utah. So.
You know, I got to give you props for that. I don't think I would enjoy driving that part. Well, wait, I'm going to do that.
That's right. He'll do it tomorrow. I love it. All right, guys. Have a good week.
Thank you.
Bye, guys.